All right, now we know what a null hypothesis and an alternative hypothesis are. A research study wants to determine if the alternative hypothesis holds. How does it do that? One way is to use randomness. Let me try to explain by going back to the example from the last video. The research study in the last video was about promotion decisions in banks. Under a male manager, is there a prejudice against women in promotion decisions? Does gender actually matter? Are fewer women promoted? This was the data, and it produced a sample statistic. Men were promoted at a rate of 87.5%, and women at a rate of 58.3%. The difference was 29.2%, or 0.292 as a proportion. So here's the question. Could this just have been random? This is a sample statistic. It captures something about the parameter on the whole population, but it's only a tiny piece. Maybe this is just a random chance that these particular cases happen to have this behavior. Maybe this sample has more men that were promoted, but another sample may be just as likely to have more women who are promoted. And this gets back to the hypotheses. The null hypothesis says that there is no relationship in the parameter, in the whole population. A sample can still have a difference, since a sample is only a small piece of a population. If I want to reject the null hypothesis, if I want to argue that the alternative hypothesis holds water, I need to say that the sample reflects the parameter, that is, it is representative, that it is significant, that it means something. How do I do that? I do it by arguing that the sample statistic is unlikely to be true under the null hypothesis. And this gets into probability. This course is not going to do much probability theory, but probability theory is a big part of statistics. For now, I just need to know the probability under the null hypothesis of producing my sample statistic. If that probability is small, it is evidence against the null hypothesis. It says that this sample statistic is unlikely to occur unless there is a relationship. So I need to study probability. This can be done with formal mathematics, which, as I said, is a large piece of the discipline of statistics. But it can also be done very well just by simulation. This is a brute force approach, and it's what we will do today. And let me again explain it in the example. Of the 48 cases in the study, 35 were promoted and 13 were not promoted. Of the promotion applicants, 24 were men and 24 were women. In the sample statistic, 21 men were promoted and 14 women were, adding up to that 35. But how likely is that breakdown to randomly happen? Well, I'm going to find out by doing a bunch of random selections. I'll randomly assign the 35 promotions to the 48 applicants. Take these 35 promotions, randomly split them up between the 24 men and the 24 women. Here's what that looks like. There are 35 promotions, and I asked a random number generator to randomly assign them into the two categories. These were the first few random trials. You can see that in each row, the two numbers sum to 35. I always assign 35 promotions, but the gender breakdown of those is random. I've also calculated the proportions and the difference, which is the third column. This is 10 random trials. I've even generated the same 14 and 21 breakdown as the sample, although it is a gender-switched example. I also happen to generate a situation randomly where all 24 women were promoted. Doing this 10 times is interesting, but doing this many, many, many times actually gives a very good idea of the probability. As I said, this is the brute force method, but it actually is pretty reliable. If I want to know the probability of something, I can simulate it and run the simulation thousands or millions of times, and I get a very good idea of the probabilities. So I run many, many random trials. Then I look at my sample statistic, a 0.292 difference in the proportion of men and women promoted. Then I ask, how often does this happen? How often do at least 29% more men get promoted than women if the promotions were actually split up randomly? The answer, after doing many, many random trials, is about 2%. This is called the p-value of the sample statistic. It is a measure of how likely it is that that statistic is the result of random chance in a varied population. So, from the sample statistic and the mathematics of random trials, I can say that there is a 2% chance that the null hypothesis is true and that there is no relationship in the population as a whole, and this sample statistic is just a random occurrence. All right, what do I think about this 2%? It certainly could happen. 2% chance things do happen. Indeed, they happen 1 time in 50. So it is possible, but it is unlikely. Evaluation of statistics is all about what is likely. We approach truth by probability and approximation. Statistics doesn't conclude that a claim is true or false. It concludes that a claim is likely or unlikely. As such, it always involves a judgment call yet again. In a statistical analysis, we get to set a significance level, and this is usually written with the Greek letter alpha. It is a measure of what we consider very unlikely. Then, if the p-value of the sample statistic is below alpha, then we consider the sample statistic to be very unlikely to have been caused just by random variance. The most common choice by far for alpha is 0.05. That means a situation which is less than 5% likely due to random chance are considered significant. In this study, the p-value is 0.02, which is indeed less than 0.05. So, by that standard, this sample statistic is considered statistically significant. As statistically significant, it is justification for the study to reject the null hypothesis and argue that the alternative hypothesis must hold. According to these conventions, this study does provide real evidence of a prejudice among bank managers to promote fewer women. This is a judgment. The 5% significance is a convention. If a higher standard of justification is needed, this can be dropped maybe to 1% or even a fraction of a percent. It's all about probability, about likeliness. But this is how hypothesis testing works. A sample statistic is generated from a sample. Some math or random trials are done to figure out the probability of the sample statistic being just random, just noise. If that probability is low enough, then it is very unlikely that the sample statistic is random chance. If this is the case, it is called statistically significant, the null hypothesis is rejected, and the study gives real evidence for the alternative hypothesis. This video may be the very heart of this course. Statistical significance is the real story behind so much of statistics. What is likely to be true? What is likely to be random? What is likely to be noise? And how do we measure all of that? This is what it's all about.